Hello, in this short video I will be going over step by step how to design steel members in our AISC steel add-on module for RFEM. In this first part I will get into how to set up the general data, and then in the next part I will go over the results portion. So as you can see right now in our graphical area, the structure I'm going to be working with for this example is a moment frame. With an RFEM we can get the general analysis of this moment frame, but what I would like to do is design these two columns in this beam to be optimized, and to do that we can use the RF Steel AISC add-on module. To access the add-on module you can go into the project navigator on the left side here and double click it. So as you can see, the add-on module is basically just a dialog box, and in this dialog box for this video we'll just be going over this input data and what you need to do to set up everything in here before you run your results. First thing I would like to do is select the columns, because these are the first things we're going to design. Then I would like to pick which method we are going to use. We're going to use LRFD. And then the next thing I would like to do is, under the Ultimate Limit State tab, is choose our load combinations that are only for LRFD, move those over to the right, and then I would like to rename this case columns. We'll click OK, and then basically everything in this general data section is filled out and complete. We're not going to worry about serviceability limit state for the columns. So the next thing we can do is move on to materials. For materials, we're going to select steel, and as you can see, these materials are automatically brought into the add-on module and we don't have to do anything further. The next section I'd like to move on to is cross sections. The same thing can be said for this section from materials. They are automatically brought in from RFEM, so we don't have to do anything here. The next information I'd like to move on to is the intermediate lateral restraints. Here we're going to define lateral restraints for the top and the bottom flanges. So if I would like to do that for either member 1 or 3, I can just check off this box and then choose the restraint type. I can choose between having lateral and torsional restraints, just the upper flange and the lower flange, or I can also do user defined. For this example, I'm just going to keep it as both the flanges. And then you can see over here I can adjust the number of lateral restraints I would like to have equally spaced. Since they're equally spaced, you can see this is giving your spacing here, which you can have them unequally spaced if you would like. You can choose which distance you would like to apply for the spacing between each of them. This next section is for effective lengths. This is for stability check. And the first thing we have is our strong axis buckling, and then our weak axis buckling, and then our torsional buckling, and then lateral torsional buckling. We'll be designing these members per the direct analysis method per chapter C. The code shows that we can set the effective length factors equal to 1.0, so we leave all of the factors as 1. Now we have to adjust the unbraced lengths, which are going to default as the full member length. Unbraced lengths are incredibly important. You want to adjust these unbraced lengths based on how your members are braced, whether that be in the strong axis or weak axis. For this video I will just assume it is the full member length that is unbraced. You can see the design parameters are just some additional variables such as the CB factor. This is normally set to 1.0 as default, which is a little more conservative, but that is only used if you are basing your lateral torsional buckling off of chapter F.1-1. Right now our lateral torsional buckling is being determined by an eigenvalue analysis, or you can change this to according to chapter F if you would like. If you would like to do that, you can do that under the effective lengths and under lateral torsional buckling. Other design parameters are listed here, such as shear length, gross area, shear distance, gross area, net area, shear lag factor, and the effective area. So that is all for the input data for our columns. Now I would like to create a new case for our beams. I'm going to save the changes. For the beams, I'm going to go to Design Of, hit this button, and then I'm going to select our beam. For this case, I would like to design it using the serviceability limit state, and then I'm going to go under serviceability limit state tab right here, and then I'm going to select only our serviceability limit combinations and result combination. Move those over. So that is it for the general data. Materials, these are already imported in. Cross sections, we don't have to change anything. Intermediate lateral restraints, we'll keep those on the top and bottom flange. Our effective lengths is unchanged, along with our design parameters. And then under serviceability, this is what is going to be different for our beams compared to our columns. This is how you're going to check your deflections. So now we can go in and select our members graphically. We're going to choose reference to member, member number. We want to choose beam. We are going to keep the reference length as the full reference length. You can change this manually if you would like. And then you can set this beam type to beam or cantilever. So now the question is, what is this going to be compared to? Well, we can go under the Details tab. And here's where we can adjust our limiting deflection up here under the Serviceability tab. Right here is where you can change your serviceability limits, such as your L over 360 for your limiting deflection. Or if you have a cantilever, you can change your L over 180 over here. Relativity can be changed up here. You either have the option for shifted member ends or the unreformed system. The shifted member ends, the deflection will be measured from the new distorted shape of the member, where the undeformed option will measure deflection from the original structure location, and it is up to you as an engineer to decide which option to apply. Either one will give you completely different results. So we'll leave this as default. Click OK. And then this pretty much concludes the first part of this video, where I basically just went over the input data for the RFEM AISC module. I hope it was helpful, and in the next video I will go over how to run and analyze the results.